Good. Let's get started with our second presentation in the second day. So it's my pleasure to introduce Sergio Grammatico from TU Delft. Actually, we invited Sergio for summer school in 2020, and you kindly accepted, but then we had to cancel the event because of the COVID. But now we are very lucky that, again, now this time we have a chance to have Sergio at the TU. Thanks, Sergio, for coming. So a bit about Sergio. Sergio is currently an associate professor at TU Delft in Center for Systems and Control. So a bit about Sergio's background. Sergio received bachelor degree in computer engineering and then master and PhD degrees in automatic control, all from University of Pisa. So PhD from 2015, if I'm not wrong.
13.
13. Oh, cool. And then you've been postdoc at ETH in Automatic Control Lab for 2 or 3 years, and then you moved Netherlands. So you've been assistant professor first at TU Eindhoven and then at TU Delft until 2018. And then since then you are associate professor at Center for Systems and Control. Sergio had, though he's very young, but already he got several very nice grants and awards. Among others, Sergio is the recipient of ERC Starting Grant, which is maybe the most prestigious grant for researchers in Europe. And Sergio, at the same time, is editor for several conferences and journals, among others, IEEE Transactions and Automatic Control, one of the flagship journals in the field of control theory. So Sergio, thanks for coming. The stage is yours. And yeah, thanks. I leave it, I don't know, here. So maybe this group will ask the first question. Yeah, ready. Thanks for coming. And then you will pass it when you have a question.
Thank you very much, Jalal. And would like to thank the organizers, so also Spiros and Pierre, besides Jalal, for inviting me, for organizing this fantastic school. So today I would like to talk about game theory and how we can apply game theory to energy systems. And we will take a mathematical route to do that. And I will try my best to give you the basic ideas on how to use math to then apply game theory to engineering systems. So let me start with the reference material that I would like to suggest specifically to today's lecture. I will start off with a recent work we did in applying game theory to energy systems. And this will serve us as a motivation, as a first case study for game theoretical models. And then I will try to characterize the math behind the use of game theory in engineering. And for that, I will use tools from operator theory. Okay, it's a branch of mathematics that is quite fun in my opinion. And here I refer to 3 references, and I would like you, if interested in the topic, to start from the one listed first, so Rio Boyd, a primer on monotone operator theory, and then move to a recent survey, fixed point strategies in data science. And in light blue, I have highlighted a book on operator theory. So it's a very, very comprehensive book. There are many results, theorems, and proofs, and then definitions. In my group, we really love this book, so you're highly recommended to have a look there as well. And then in the last part of today's lecture, we will talk about special classes of games, aggregative games and network games. And for that, I would like to refer to a recent paper of ours. And the last one on the list is going to be published on the Control Systems magazine soon. And anytime you have a question, please feel free to interrupt me. Let's see if this goes forward. All right, let's try again. Seems a little stuck. Okay, so I thought about dividing today's lecture in 4 main parts. 2 to be addressed before the break and 2 after the break. And finally, a section on concluding remarks and outlook for future directions. So we will start off with an application to power grids. So some motivation on game theory, introduction, some examples, and an application. And then we will dive into the math, okay? So our first step would be how to apply game theory via operator theory. And the second step would be how to then solve the game that we formulate. And then finally, in section number 4, we will look at the class of aggregative games, as I mentioned earlier. All right, so let's get started. And let's discuss why we speak about game theory today. So my view is that we use game theory and models based on game theory to model complex systems, so complex infrastructures that have special features. And those special features are that there are possibly multiple decision makers, okay, multiple agents, multiple subsystems that are possibly selfish, okay, so interested in their own objective, their own revenue, their own cost function. And we will refer to those decision makers as agents. And the key feature in many engineering systems is that those agents share resources. Okay, so think about the power grids. You have shared physical network, but possibly different agents that have their own revenue function in mind to maximize. And there are actually many applications where this happens. For example, in wireless communications, our devices share the Wi-Fi bandwidth, but also in control when subsystems make collisions in order to improve the overall performance of the system, and smart grids as well. In fact, game theory has received quite some attention in the applied mathematics and engineering domains. And so people have studied how it connects to optimization, variational inequality, and we will see a bit of that today. So let's start off with one example, okay? And this is taken from energy systems. And the example is demand-side management. So how many of you is a little bit familiar with demand-side management? Please raise your hands. Okay, perfect. So the idea is that we have a figure here on the, let me see if I can point, maybe, yes, we have a figure on the right side. And that's the typical energy demand during a day. Okay, so there is a valley during the night where, you know, we're supposed to consume less electricity unless there is a, you know, a conference deadline the day after. And there is a peak in demand during the day. Okay, typically when we come back from work, we come back home and we start activating all our devices. And we have many agents in the picture, many prosumers. We will define the notion of prosumer a little bit better soon. And we would like to desynchronize or flatten the overall energy demand. That's good for the distribution system operator, okay? So suppose that I give you this background demand, right, with a valley during the night and a peak around 3 p.m., so in the afternoon. And suppose that each of you is owner of an electric car, okay? So you can choose the electric car you like the most, and you have to choose when to recharge your car, given that the price for electricity that you pay is proportional to the overall demand. And we said the electricity demand is low during night and high during daytime, okay? So if you have full freedom on in which time slots to recharge your vehicle, given this variable price, when would you like to activate the charging? So who would like to guess?
In the night?
You would do it during the night. Who else? You as well, right? You said during the night as well. Who would do it during the night, valet? I mean, price is going to be proportional, right, to the demand. Everybody would do it during the night. Who would not do it during the night? You would not. Why not? Sorry? Right. So suppose you do not have roofs. Yeah, good observation. Yes? It could definitely depend on the season, but here for simplicity, we're assuming we have this demand forecast that says we are in a standard season and it's going to be low demand during night, no conferences, no deadlines the day after. All right, so you wanted to say something? Exactly. So that's the point that I would like to make. So we're around 60 people here, so it's okay if everybody starts to charge at what is it 3 a.m. in the night. But suppose we are 5,000 people, right? And at the very same spot, there would be a huge peak in electricity demand because everybody wants to charge their car when they expect the prices to be low. Okay, and that's the trickery around game theory. Okay. So each of you has a monetary objective in mind, right? I would like to pay as little as possible to recharge my vehicle. But this price here, since it depends on the overall demand, is somehow affected or is influenced by the decisions of your peers. And as long as we are 50, it might be okay for the distribution system operator, but if we're 5,000, all located at DTU campus at the very same time slot, that might create a peak in demand and therefore high prices, okay? So this is to say that the decision problem is not that trivial. It's not a unique optimization problem where we decide for all of you when it's best to recharge your car. It's really dependent on each other's decision, right? Okay, so in more general terms, imagine that on top of paying a sort of congestion cost that we just described, you also pay some discomfort cost in changing your habits, and you're subject to some limits. Okay, there are charging rates, or for example, you really do not want your washing machine to be on during the night just because it's cheap, and so on and so forth. Okay, so you might think that each prosumer has a sort of optimization problem in mind that has the key feature that both the cost as well as the constraints depend on the optimization or the decisions of the other prosumers. Okay, and in fact, this demand-side management problem has been addressed more than a decade ago in the smart grid community, in the signal processing, and a little bit more recently also in operations research and control. All right, a second example that I have, again inspired from energy systems, actually from energy markets, is that of day-ahead markets. So here we have a slide where electricity markets are nicely visualized. Electricity markets in the Netherlands are nicely visualized. So the idea is that you have day-ahead markets where energy companies and system operators agree or optimize a certain predicted schedule for the day after. And then you have a real-time phase where this ideal schedule is somehow readjusted based on real-time needs. And the next slide, we're going to focus on the day-ahead market because it has a static flavor, while, as I said, much more is going on in real-time markets for balancing, for example. Okay, so what happens in simple terms in a day-ahead market is that you have multiple generators on the one hand, and on the other hand, you have a system operator. Okay, And they try to come to an agreement that is beneficial for all. Okay? So let's see what the generators have in mind. Well, the generators would like to maximize profit, right? So they would like to sell the electricity they produce, subject to engineering limits on their operation. So ramp-up limits, maximum capacity, and so on and so forth. So the cost function of a generator looks like, you know, amount of energy, electricity sold, so prices times quantity of energy sold, negative the cost they have to pay for this generation, negative the fees they have to pay to the system operator for generating a local imbalance, okay, an imbalance between what they sell and what they generate at the same node. Okay, and we might have many generators in the picture. And on the other end of the spectrum, we have a system operator that also wants to maximize some revenue function by changing the fees imposed on the generators and subject to some engineering limits. For example, some transmission capacities. Okay, so you want your lines not to exceed their capacity, not to get them overloaded. And so what do we observe here? So we have the decision variables of the generators in blue, and we have the decision variable of the system operator in red. So who can spot the key features of those optimization problems? Any guess from this?
Doesn't the
Yes.
system operator want to minimize the total system cost?
It could be an alternative cost function, yes. Yes. So you can imagine this revenue function is based on that as well. But it will not change the structure of the optimization problem in terms of key features. So can anyone spot the key features we have here?
Competing optimization problems.
Yes, what do you mean by competing? Very well.
The system operator tries to maximize its revenue.
Yes.
But if it maximizes revenue, then the market itself, the objective function will grow.
Right. So it's so put in slightly different words, the objective function of the system operator, whether it is some revenue function or the overall system cost, might be disaligned with the individual objective of the generators, right? Yeah. Very well. And what if we look at the constraints? Sorry?
Network constraints.
We have network constraints, yes. What feature have those constraints, especially the constraints that the system operator is looking at?
Non-linear.
There might be no linear, yes. In terms of dependencies?
Oh, yeah, it depends on the other problem.
Exactly. So the system operator is mostly interested in having the transmission capacities under control, right? So the transmission lines should not have their capacity exceeded. But this depends on the decision variables of the generators, right? It's not the system operator that decides how much the generators are going to sell and generate at the different nodes, right? So those constraints somehow are shared among the generators, and the system operator should take a close look at those constraints, okay? So again, we have a situation with multiple decision makers, objective functions that relate to each other, possible not directly in line with each other or compliant with each other, so possibly in competition, as your colleague said, as well as the constraints are somehow shared between all those parties, okay? All right, so there might be many, many other examples of games, right? So a set of optimization problems that relate to each other. And I would like to ask you if you have some example in mind about such scenarios. Feel free to raise your hand. So any example, any idea on scenarios where you have multiple decision makers, multiple agents, whose objective functions might collide with each other? In communication? Perfect, that's very well, very good. Other examples? Yeah. Yes, in security, you might have attackers on the one hand, defenders on the other hand, and in order for the attacker to remain stealthy, so not directly discovered, it might need to compromise a little bit the objective function, their own objective function. Yes, correct. Other examples from everyday life? Gambling? Why? Why is that?
So I mean, it's like whether you earn money or not depending on the decision of others.
Yes, yes. That's why we call it game theory. Yes. Other examples from everyday life? Well, unless.
Any producers?
I'm sorry, I didn't hear.
Pricing policies for any producers, how they want to price a product, for example.
Correct, correct.
In a competition, same category.
Exactly. Competition in pricing products, that's correct. Other examples from everyday life, perhaps Denmark and the Netherlands are not the best examples because many people bike. Other examples? Yeah.
Transport and logistics.
Yes, transport and logistics, transportation, and road traffic, right? In road traffic, you have different drivers with their own objective, right? Get from A to B as soon as possible, or I don't know, save fuel. And congestion levels on the roads are based on how many drivers choose that road. And somehow it loses connection every now and then. Let's try again. Yes. Yeah, so road traffic is another clean example of engineering application where game theory is very relevant because you have different vehicles, each one with an objective function in mind, say minimize travel time, and this depends on the congestion levels. But the congestion levels depend on where the other drivers want to go, right? Or are planning to go. And so what we do in road traffic control is to try to alleviate congestion by using traffic light control, ramp metering, or tolls. But if we look at the individual vehicles, you see many agents with objective functions colliding with each other subject to constraints. Okay? So that's another example of game theoretic application domain. All right. So we have introduced many examples where game theory is applicable, but what do these examples have in common? So here I listed a few features. Well, in every case, we had many autonomous subsystems. Okay, so each subsystem could decide by their own. Okay, so no system operator can force you to charge your electric car or turn on your electric devices at a certain time of the day. It's your own choice. So you have decision authority. Those decision makers are self-interested. Okay, think about markets with energy or service companies, possibly large scale, so hundreds or thousands of agents. The fourth bullet point is about locality of information or privacy, which means that each decision maker might want to keep their private information private, right? You don't want to reveal your habits to your neighbors just because this is good for the overall network. And in some cases, we can have disruptions if we leave those systems uncoordinated or uncontrolled. Okay? So what are two typical examples of disrupted systems or disrupted infrastructures when all those selfish decision makers do not coordinate well with each other? Yes? Yes. Yeah, that's very much correct. Policy making, that's very important, yes. On a very shorter time scale, what could be other examples from everyday life?
Car crash.
I'm sorry?
Car crash.
Yes, so traffic jams. So car crashes induced by traffic jams and power outages. Okay, if we saw the line capacities, if those are exceeded, then some lines may overheat, and therefore we have a power outage. And yeah, well, traffic jam is experienced quite often in our everyday life. Okay, so another application that I would like to talk about now is the power dispatch problem in smart grids and how we can model that as a game. So who can give me a brief introduction about the power dispatch problem, what it is, or what it's supposed to do? Anyone?
Minimization of total system costs and technical constraints such as power constraints.
Yes, so that would be the objective, but what we would like to do is to dispatch or schedule power generation all over a certain portion of the power grid, subject some cost is minimized, or subject to all the parties involved are happy with their revenues or with their generation, subject to engineering constraints, right? Okay, so we can model that as a game in the following way. So we have n prosumers, okay? So entities that can produce as well as store as well as consume electricity. For simplicity, let's say we have one distribution network operator. We might have local constraints. We might have power balance constraints. There could be the option that the prosumers are allowed to trade with each other. Okay, so they trade locally, or they can trade with the main grid. And so when we put all those features together, if we think again that each prosumer has their own objective function in mind, then we get a game. And here we call it market clearing game. Okay, for reasons that will be clear in a couple of slides. Okay, so the picture on the right summarizes that we have a physical grid, and in blue we see a possible trading network. Okay, so we have prosumers that might trade electricity with each other, and then we have algorithms that make sure that those those tradings are well coordinated. Okay, and those algorithms include both the interaction between prosumers as well as the interaction with the main grid. Okay, so let me be a little bit more specific. By prosumer, we mean an energy consumer that can store and produce electricity. And there might be different types of prosumers, dispatchable, for example, fuel-based generators that have their own operational constraints. There might be storage units with their own dynamics, in terms of with their own storage dynamics, and simple passive prosumers that just consume electricity. Okay, so those are the traditional consumers. Then we need to make sure that there is power balance at all times. So the local power demand should be equal to the local power inflow, including all possible sources of power exchange. So from the main grids, the storage and the local generation, the trading. And we can think that each prosumer has an objective function in mind, which is typically a convex function, okay? Or even a quadratic function. And we're going to call this Ji. Okay, so if we look at the physics, so those were the prosumers. If we look at the physics, we have power flow constraints, okay, power flow equations. And we know, as your colleague pointed out, that those are nonlinear or non-convex. And in many cases, we look at linear approximations or convex approximations to make the problem easier to solve. And those are enforced at each bus, okay? And we might also have reactive power equations, capacity constraints, and voltage, phase and angle constraints, etc. Okay, so many engineering constraints into the picture. The second part is a bit more exciting in the sense that if we allow the prosumers to trade electricity with each other, then we might have some constraints and objective functions that refer to the energy trading. Okay, so there might be a cost for trading with your neighbor, okay, for peer-to-peer trading, and you might describe the energy trading itself with a bunch of constraints, saying that what I trade with you is equal to negative what you trade with me, okay? So to enforce peer-to-peer trading via constraints. And of course, there might be trading with the main grid as well, as we're all used to. And yeah, typical feature in a smart grid, once again, is that the electricity price you pay is proportional to the total demand. We saw that in example number 1. Okay, so when we put all those ingredients together, so remember the prosumer characterization, the physics characterization, and the energy trading characterization, we come to this power dispatch game. So for each prosumer, let's say that xi in blue is the vector of energy allocations over a certain time horizon, say 24 hours. Each prosumer has an optimization problem, pi, to solve. It's an individual one, okay? So essentially, the prosumer wants to minimize the cost function ji, subject to local operation constraints, subject to the power flow equations, and subject to trading constraints. So I've highlighted these 2 classes of constraints in red here. Okay, so take a moment to look at that. And I would like to ask you why I made these 2 classes of constraints highlighted. Any idea, any guess? Yes? Exactly, because those are shared constraints, okay? So quantities or sentences in red today's morning will be typically things that are hard to deal with, okay? So coupling constraints and variables that are shared among the agents. Okay, so mathematically speaking, this power dispatch game is essentially a set of optimization problems, P1, P2, Pn, that are dependent with each other. Okay, so those are interdependent optimization problems. Yes, please. Yes, that's a very important question. So I have a dedicated slide for the notation, but I'm happy to take this question already now. So we are going to put the subscript to indicate the agent. Okay, so xi is going to be the vector, the decision vector of agent I, right? And might be a vector in Rn, but it's going to be finite dimensional. There's a funny notation there that you might have noticed in magenta that I was planning to clarify later, but I think it's important. It's nice to clarify already here. So this x negative I, it means that we take all the decision vectors from all agents except the one of agent I. Okay, so if I is equal to 1, xi is going to be x1, and then x negative 1 will be x2, x3, x4, and so on and so forth, all put together in one very, very long vector. All right? Any question on the notation or the formulation of the problem? Yes, please.
Is it allowed to push the energy back to the main grid?
No, not in the model that we presented in this paper, but mathematically it could be possible, yes.
And from the game theory perspective, does it change anything in the optimization?
No, not in the structure of the problem itself. No. You would need to, let's say, if you penalize or reward such an action, you might need to put a convex function to this energy transaction. But apart from that, it will not alter much the structure of this optimization problem PI.
Price drops and demand drops.
That would be a consequence of such a term that you will observe in the solution of the game. But the modeling of the game itself will not change much its structure. And we're going to see results in the next slides. Yes, please.
Here we have the optimization problem for the consumers, but is
Yes.
there one also for the distribution network?
So not in this simplified model, but you could very well think that there is an additional agent that somehow plays the game and is the n+1 agent involved. Okay. But for simplicity here, I didn't put the optimization problem of the system operator. Any other question or remark or comment? Yes, please.
I didn't get the components of xi. Did you then
The component is going to be different times of the day. Okay. Yeah. So the subscript means is the index of the agent. Then xi is going to be a vector, say a vector of n components or 24 components, each one representing the energy that you allocate in that time slot. Yeah. All right. So let's see what happens when we use this model. Solve the game. Okay, I was not specific enough yet to explain what I mean by solution of the game. We will get there later today. But let's see what happens. Let's see if there is any benefit in solving a game for some toy networks. So let's take this example with 12 prosumers, 15 passive loads, and say we have an energy trading network. So those prosumers might possibly trade with each other. Let's see what happens. So the first result we observed is that if we do not put the transmission capacity constraints, okay, so if we don't put a limit on how much power can go to every line, then penalizing linearly, let's say the electrical congestion levels is not necessarily enough to avoid overloading. Okay, so on the left side you see what happens when we impose the physical constraints into our model. Okay, so all the lines are within their nominal capacities. If we take those physics-based constraints out, then we might have some overloading. Okay, so the penalization via the cost is not necessary enough. The second observation we make from the simulations is that when you allow energy trading between users, then each of them or most of them does benefit. Okay, and why? Because we have more degrees of freedom given to each prosumer, and trading in almost all cases turns out to be beneficial. So they can save, the blue bars refer to how much they save in terms of cost in the presence of energy trading versus without the option of energy trading between them. Question? Yes?
On 2 slides before, on this trading scheme, was it a result of the optimization, or this is what was allowed?
No, this was what was allowed. Yeah. So there might be some other trading network. This was just a given one. Okay, so we're not optimizing for both the dispatch decisions as well as the trading connections, but we're saying, given those trading connections, this is the outcome of the game. Okay. Oops. No. Okay. All right. So the other observation we made is that local storage helps to reduce peak shaving, and that was kind of expected if we make use of storage, because we can utilize the storage when we have valley times in order to reuse it again during peak times. And this is another observation that we made, essentially based on the game structure, and we're going to see later that it is an aggregative game structure, because we said the electricity prices depend on the overall demand. Then we observed that when we run an algorithm to compute a solution of the game, then the number of steps it takes for the algorithm to converge, essentially to find a solution, is more or less the same over the number of prosumers. Okay, so it's not that if the network is larger, then we need more time to let the algorithm converge. But thanks to the game structure, the aggregative game structure, and we will zoom in this feature in section number 4, then we can keep the number of iterations needed for convergence almost constant. Question? Yes. I'm sorry? How do we know that that's the only solution? Yes. We actually, we do not know in advance, meaning that given the assumptions that we have on the primitives of the game, there might well be more than one solution to the game. And so a natural question is, if the math tells us that there is more than one solution, how do I pick the one of interest, the best one? Okay? And I have a slide on that at the very, very end as one of the Outlook research directions we recently took. That's a very, very well-posed question. All right. In this special case, the objective functions were such that there was a unique variational equilibrium to the game. All right, so let me check if my pointer decides to work again. No. All right, so in the next section, we're going to see how to apply game theory, okay? And I like this scheme very much because it really summarizes the steps that we're going to take, okay? So in the bottom left, you see that we start off with a game equilibrium problem. For example, example number 1, or the day-ahead market that we saw, or the power dispatch game. And this game is formulated as a number of optimization problems. Now, we would like to find a solution of this game, and are going to be specific on what we mean by solution. And to do that is extremely hard to come up with an algorithm and then use math to prove whether or not this algorithm is supposed to work. And so in order to come up to a solution, we're going to take a two-step procedure, essentially the 2 steps on the top. So first, we're going to reformulate the problem mathematically. Okay? And second, given this mathematical representation, we're going to directly synthesize or design an algorithm that is by design supposed to give us a solution to the game. Okay? So I would like to stress that the approach is not about proving that a certain algorithm works, okay? But the approach is to create a mathematical framework such that the algorithm is directly designed to be working, okay? So the 2 steps on the top are a little bit challenging, so I have to warn you in advance, but in my opinion, very fun, and also the result, so an algorithm with proven convergence guarantee, is also a very nice achievement. Okay, so let me give you some notation in order to get started. We saw that a little bit already, so we have n agents. Xi is going to be the decision variable of agent I. When I use bold variables, I mean all the variables together, x1, x2, down to xn. So I will refer to like all decision variables, to that as all decision variables. X negative I means all decision variables except that of agent I. And we're going to have a number of optimization problems, as you might have guessed already, where the cost and the constraints are interrelated. Okay? Okay, so let's start off with a simple game, what I call the simplest congestion game, where we have only 2 agents. We have, say, 1 resource, which means that x1 and x2 are just one-dimensional decision variables. And let's say that x1 should live in the interval 0, 1, okay, where xi equals 0 means that we do not use the resource, and I equal to 1 means that we use all the resource available. And same holds for agent 2. And say that we impose a limit on this resource, right? So x1 plus x2 should be less or equal than 1. Okay? So this resource is shared. So on the right, we have the feasibility set of this game. So in blue, we have the interval 0, 1 for agent 1. In red, we have the interval for 0, 1 for the variable x2. And in green, we have the shared feasible set, right? So x1 plus x2 less or equal than 1. So we would like to take x1 and x2 within the green area, including the blue and the red, such that, say, both agents are happy with their decision, where happiness is measured via this objective function, okay? So let's say that agent I wants to minimize a trade-off between a local term, okay, which is the Euclidean distance from some reference use of the resource, okay, xi ref, and a sort of congestion term, okay? So we can think that x1 plus x2, the one in here on the right side, is a congestion price, and xi is the quantity that we choose to use, right? So the more resource we use, so the higher is xi, the higher we pay for using it, okay? So this congestion price is proportional to the overall use. Any question on this congestion game? Yes?
So, like, should the x1 be like a variable here, or should
I'm sorry?
like that, for example, for x1, is this a
Yes.
parameter here? Or
Yes, this is supposed to be a variable. So I might have highlighted that in blue. But the reason why it is not in blue is that this congestion price term is the same for agent 1 and agent 2. But definitely if I is equal to 1, then that x1 should be in blue. Yes, and x2 should be in magenta. Good observation. Yes?
What is xi ref?
Is a reference use for the resource. Okay, suppose that there is no congestion price, that you can choose how much resource you want to use, then xi ref is the usage that you want to take. It might be equal to 1, or perhaps you have some other limitations, and therefore xi ref might be equal to 1/2. Okay, it's any value in between 0 and 1. Okay, so what do we mean by game? I think we saw that already a number of times, and we're quite confident now we understand that a game is a collection of those optimization problems where we might want to differentiate between local constraints, so constraints that refer to the local variable only, xi, and constraints that are coupled, so or shared, constraints that refer to all or a set of decision variables, okay? And I've highlighted that line in red. Okay, one possible solution concept for a game is to find a set of vectors, x1 star, x2 star, x3 star, such that all those optimization problems are simultaneously solved, okay? So they're all solved. And how would you go about solving such a game? So how would you go about finding such a vector of vectors, x star, such that all the problems are simultaneously solved? Any idea, any guess? Yes, iterative. For example, which iteration would you try out? So suppose that let's warm this up. Suppose I give you one tentative x star. Let's call it x star 0. Okay. How would you look for another guess in case my guess is not already a solution to the optimization problems.
I would take another x which is also in the feasible area.
Yes?
Compare my solution to this one.
Yes?
And then go on.
Yes. So you would take a random other point in the feasible area and compare and check whether or not this new random point solves of the optimization problems. Okay, that's fine. But if the feasible area is infinity, in this case infinity power 2, then you will need to try many points, right? So many points. Yeah, sorry?
Gradient descent.
Yes, but we have no gradient here, right?
No.
If we had one optimization problem, then you have the gradients, and then you go through that, right? Here we have many optimization problems, many gradients, but that's a very good try. Yes?
So you would also say maybe something iterative?
Yes.
So you start with the feasible points,
Yes?
and then you solve the problem, fixing the variables from the other players, and then you solve it for yourself, and then you go to the other one. The same thing. In this way, you proceed to.
Yeah, that's very, very good. So those are the best response dynamics, okay? So I give you a guess. You put this guess in the magenta variable, so you fix the second argument of the cost as well as the second part of the constraints. You optimize all those problems. You get new blue variables, and that's your new guess, okay? That's the best response to the given ones. That's very good. And there was another attempt here, or not? Someone-
Exactly the same. Or maybe we can try one master problem and two separate subproblems for each.
Yes. The difficulty there could be that if you have many, if n is large, then the number of master and slaves grows very much fast. Yeah. Okay. So the best response dynamics is a very good idea. Also, the gradient dynamics is a very good idea, but we will need to modify them a little bit because none of the two are supposed to converge. It might be that when you iterate the best response dynamics, you oscillate forever. Okay. So let's see how we might do that. Okay, so let me formalize the notion of solution first. So we said we have a solution of the game where when we find a set of vectors that simultaneously solve the optimization problems, and this is essentially the notion of Nash equilibrium, okay? Essentially a fixed point of the best response operator, okay? So if you freeze all the magenta variables and you optimize all the problems, you get the frozen variables again in blue. So you find a fixed point of this best response mapping. In the original paper by Nash, you have a definition of Nash equilibria without coupling constraints. Okay, the constraints in red. A couple of years later, the coupling constraints were introduced, and soon afterwards, we see the birth of mathematical economy. And so the original application of game theory was indeed economics. Okay, in the case in which you have coupling constraints, in the so-called generalized Nash equilibrium case, then I would highly recommend you to read the survey paper by Facchini and Canzo, where in the convex case, we have definitions as well as the first set of algorithms that are supposed to give us a Nash equilibrium, okay, together with existence and uniqueness results. Okay, so I would like to do a couple of more slides before the break. When going from Nash equilibria to generalized Nash equilibria, the key difference in the definition is that we look at games with coupling constraints. That's why we call it generalized Nash equilibrium. And as we saw in the congestion game, the feasible area, the green one, was not decoupled, right? So it was really shared between the two agents and hard to decouple. So for example, if I gave you one random point outside the feasible area, in order to find a feasible point, even finding a feasible point was hard because projecting in this green area involves a computation for both players together. Okay, you cannot ask one agent to do that and then the other agent to do that because the set is is coupled. So when you have coupling constraints, okay, and you want to make your computations in your iterative process, even the best response dynamics, how would you decouple the computations given that you have coupled constraints? How would you go about decoupling the coupling constraints? Yes?
We will relax those coupling constraints and add to the objective using Lagrangian functions?
Exactly. We would use Lagrangian duality in order to treat those constraints as part of the cost function and therefore deal with something that looks without coupling constraints and then look for the best dual variable. Okay, so let's do that. So we would do that via Lagrangian functions. There is a catch here. The catch is that in optimization, we have one objective function, therefore one Lagrangian function. In games, we have many optimization problems, so many Lagrangian functions. Okay, so one for each agent. So in general, the Lagrangian function can have those three terms. So the cost function ji, the indicator function to represent the local constraints, and the third term, which is what your colleague said. So the dual variable that here we call lambda, it's in red, meaning that it refers to the coupling constraints, that multiplies the function describing the coupling constraints. I have a question for you. Who can recall what is this iota function, so the indicator function of a set? Who knows what is the indicator function of a set? Yes, please. Exactly. So the indicator function of a set is a function which is flat in the set, is equal to 0, and equal to plus infinity outside. And this is a way of saying that, well, if you take xi outside the constraints, then you get a cost plus infinity. And who wants a cost to plus infinity? Nobody, right? So we really need xi to be within the feasible set. Okay, that's a way to move those constraints in the Lagrangian function. Okay, so some of you may have heard about the KKT theorem. Yes, question? So that's a good observation, and we will talk about convexity in a second. So the indicator function is defined even if your set is non-convex. So equal to 0 in the set, plus infinity outside. If the set is convex, also the indicator function, as weird as it looks, is a convex function. All right? All right, so some of you may have heard of the KKT theorem. Okay? Who has heard of it already? Raise your hand. Okay, very good. So in case we have some regularity conditions, some convexity, then we know that our xi solves the optimization problem pi if and only if the KKT system is satisfied. And here I just list the conditions. So essentially we need stationarity of the Lagrangian. So when we take the derivative with respect to xi, we need this derivative to be 0. Okay. So the inclusion symbol is just in case the function is not differentiable. If you're not familiar with the subdifferentials, think that you have the gradient there, the derivative with respect to xi. Of course, we need the coupling constraints to be feasible, the second line. And we have this weird condition, which is the complementarity condition. Okay, so we need this dual variable lambda to be orthogonal to the function that describes the constraints. And since we have inequality constraints, we want this lambda to be non-negative. Okay, I hope many of you have heard of that. Okay, so I said this works out if we have regularity conditions and convexity. So from now onwards, we're going to put a convexity blanket into our problem. So we're going to have closed convex sets with constraint qualification, convex cost function in the first variable, and an additional condition that will be a bit more clear later on. We will need that all the partial derivatives, when put together, generate an operator, so a mapping, which is monotone. And being monotone is a technical property that I don't want you to fully understand at this moment. It will be clear later on. But think that when you have a convex function, and you take the gradient of this function, then the gradient is a monotone operator. Okay? So if instead of a game we had an optimization problem, we would need this assumption anyways to be in the convex framework. Okay? When we have multiple optimization problems and therefore a game, this convexity translates into monotonicity of the mapping F. Okay, the mapping F there in green, and the mapping F just puts together the partial derivatives. Okay, so it's a byproduct of the need for convexity. All right, so I would like to do a couple of more slides before the break and before we start with some little exercises for you. And since many of you are aware of the KKT theorem, I will go through this graphical explanation of the KKT conditions quite briefly. So here I would like to explain why we need the stationarity condition, right, in the KKT theorem. And so for simplicity, assume that we have only one player. Okay, so there is only one x, no subscript. And we have no coupling constraints. Okay, the only constraint we have is this x limited to the capital omega set, which is shown there in light gray. Okay, so we want to find x that minimizes j, subject to x living in omega. And here I'm claiming that via the KKT conditions, this is equivalent to finding a solution to this inclusion. Okay, so 0 inside the gradient of j plus the, let me call it gradient or subdifferential of the indicator function. Okay, so on the top right, we see the derivative of our Lagrangian function, right? So let's go back one sec. So here the Lagrangian function had 3 terms. We do not have the third term anymore because we said we have no coupling constraints, so we're left with 2. And if we look at the stationarity condition, so the first line in the KKT theorem, we see that we need the partial derivative with respect to x of the sum of the 2 terms, right, in the Lagrangian. Okay, any question here? Any doubt? Okay, so we're going to take only the first, we're going to consider only the first line in the KKT theorem because we have no g function, so the second and the third are not considered here at all. Okay, so when we differentiate j, we get the gradient of j in red. And when we differentiate the indicator function, we get the blue vector here in the picture, which is called normal cone. Okay. Well, the indicator function is 0 in the set, plus infinity outside. You can imagine when we differentiate such a weird function, we get something also not very standard. But you can imagine that as the function is flat in the set here, the derivative is 0. If the function is plus infinity, I'm going to say that the derivative does not even exist. I'm not able to differentiate plus infinity. And something strange happens when we go from 0 to plus infinity, right? There might be a spike, and that's the spike we see in the light blue line, okay? Because the function has a huge jump. Okay, so let's look at the equation. This comes from the stationarity condition in the KKT system. We see, if we think about geometry, we see a balance between the vector in red and the vector in blue, right? This is what the equation says, and this is what is visualized in the picture. So we need to find a point x star such that we have the perfect balance between the gradient direction and the direction of the normal cone, okay, the blue direction, okay? And so this is because the gradient direction is where the function increases. So ideally, we would like to go along the gradient direction, as your colleague said, so where the function decreases. And so if we look at the picture and we look at the level curves, ideally, we would like to take x that tries to go outside the set, right, to follow negative the gradient direction. However, there is the feasible set that we should take into account. There's a sort of wall that blocks x star from moving outside. And once we reach that wall, there would be a sort of force reaction from the constraint, which is illustrated with a blue vector, okay? And so there, this balance happens, and we have found our x star, Okay, this is the geometric explanation of the first condition in the KKT theorem. Okay, any question here? Any comment? Yes, please.
This solution is like the simplest one that you only need to evaluate the points in the corners to get the optimal.
So so the solution might not be necessarily on the corners because the function j might not be linear. What I'm saying here, so I'm not giving any algorithm. I'm saying that the solution x star would satisfy this balance between these two vectors. How to find such an x star is still an open question.
No matter if it is inside of the visible on the...
Exactly. If it is strictly inside the set, then the normal cone would be 0 because it's the derivative of a function, the indicator function, which is 0. And therefore, we will just look at a 0 of the gradient. Okay? So this condition holds no matter where x star will eventually be. Okay? And other comments or questions? Yes, please.
Is it clear how to quantify the red arrow since we can calculate the derivative of the function, but how do we quantify the blue one if we don't know the value?
Exactly. So that's a good question. So that's a good point. So if we knew x or a guess and iterate x, then we can evaluate the gradient. So we know how long is the red vector, right? While regarding the normal cone, we only have the full direction, the light blue direction, right? So the question is, how long should be the vector in that direction? And in fact, this is why we have the lambda guy. Okay, so the lambda guy will be a multiplier, right? That tells us how long we should take this vector in the normal cone. Okay, and this is why here we have an inclusion. Okay, an inclusion means we would like to find a vector blue such that let's call it v, such that 0 is equal to the gradient of j plus v. Okay, we know the direction, so we can freeze the light blue direction. We do not know how far we should go along this direction, and that would be quantified by the lambda variable. I have another picture to illustrate that later. Okay, so this is exactly the reason why we have an inclusion there. It's a very good point. There was another question there.
Yeah. So basically, the indicator function, it's like a mathematical tool, but numerically you'd have to approximate it by a smooth, like differentiable function if you actually want to run the optimization like an optimizer or not.
No. So indeed, we're not going to evaluate the indicator function. We will introduce mathematical trickery in order not to do that, and instead have an operation that takes into account the fact that we have the indicator function, but this operation is a rather simple one. And
so numerically you would then just put like on an actual convex optimizer that function because that's not something that...
no.
Because your optimizer couldn't differentiate that, right?
Right. Exactly. So numerically, we're not going to smooth out the indicator function, but instead we're going to use another operation that I'm not going to spoil that makes much more sense, and you will see is quite natural in your algorithms that you have seen already. There was another point there.
So just one question is on the indicator function. Is the alternative to just include the constraints of the agent?
I'm sorry, the indicator function alternative?
As an alternative to the indicator function,
Yes.
not just in terms of thinking about this as an optimization problem, can you not just include the feasibility constraints of the agent itself?
You mean include them as the where coupling constraints, or so without moving them in the Lagrangian? You mean?
Yeah. So well, I guess.
Yes.
Can you simplify the problem to incorporate it? So you move it away from pure Lagrangian to some
Yes.
something which has
Yes, and that's
basically
it's the next slide. It's the next slide. Yes. So you can indeed decide if those constraints were part of your, let's say, local constraints with the indicator function, or if you want to place them in the g function. Okay, so g less or equal than 0 might very well encode this polytope, right? You might have g1 less or equal than 0, g2 less or equal than 0, and so on and so forth. If you do that, the conditions you get are essentially the same. The Lagrangian function will have this g function as a third term, and the conditions will be the same. Will end up to be the same, even if they look different. Yeah. Yes. All right. So what I would like to do now, before we move on with this formulation, is to have our 15-minute break, and then we will continue about this complementarity condition. All right, so we left with the KKT conditions explained in the case we have local constraints only. Here we have essentially the same conditions in case we have no local constraints but coupling constraints. And what happens in this case in our KKT conditions is that we are left with this complementarity condition, which is not the nicest constraint that I've ever seen. So we would like this dual variable lambda that somehow quantifies or prices the infeasibility of the coupling constraints to be orthogonal to this function g. Okay? And we would like to transform that into something which is nicer from a mathematical perspective as well as easier to handle computationally speaking. So the way to transform this complementarity constraint is via this normal cone operator. So I've discussed that with some of you already. It looks a bit scary, but let's try to digest that. So the normal cone operator, let's remind us what it is. It's a mapping that essentially is the derivative of the indicator function. Okay? So indicator function is 0 inside the sets, and therefore the derivative is going to be 0. That would be the point xi inside the set C. Outside the set, the indicator function is plus infinity. So when we differentiate, we say by convention that we have no derivative. So derivative is empty. Okay? So if we take a point z outside the set, the normal cone will be empty. And so interesting things happen when we are at the boundary, because the function goes from 0 to plus infinity. So quite a steep growth. So if we take a point y on the boundary of the set, the normal cone points at the direction where the function increases the most, and this direction is normal, it's orthogonal to the set. So if we take the tangent, we have the normal direction, which is the blue vector on the left side of the picture. And if we have a point which is on a non-differentiable corner, then we have many normal directions, and that's why we call it normal cone. We have a cone of normal directions. Okay, now let's look at our constraint, the complementarity constraint, lambda orthogonal to g, lambda being non-negative and g being non-positive. And I summarized that on the right picture. So we would like a condition with the normal cone, which is our favorite guy, to represent the complementarity condition, the orthogonality. Okay? So the lambda vector is in red. I took one vector which is non-negative. Okay? And I'm claiming that the condition on the left side, so the complementarity condition, is equivalent to having g inside the normal cone evaluated at lambda. Let's see if that is the case. So let's look at the picture on the right. We have lambda non-negative. The normal cone evaluated at lambda of the positive or non-negative orthant is the direction that points towards the left. Let me go here. Okay. So this is our set here in gray. The normal direction at this point lambda is normal to the set, is this light blue direction. And therefore lambda is orthogonal to the normal cone, right? Lambda is non-negative, and this vector here is non-positive. Okay, so the x1 direction is strictly negative, right? Because it points towards the left. And the other direction is going to be equal to 0. Okay? So if indeed g lives inside this direction, right? then G will be orthogonal to lambda. That's by definition a normal cone. Lambda would be non-negative. Okay? And this vector here will be non-positive. Okay, so geometrically we have shown that this guy here on the left, which looked a little scary, is equivalent to this guy here, which might be still scary, but is a bit less scary to me. and here I just moved this G to the other side to have 0 here. Okay, a condition which looks like the stationarity of the Lagrangian, right? 0 in partial of L. Okay, so we have a similar condition here. Okay, so essentially we can take this guy out and replace it by this guy in our KKT theorem. Okay, well, let's do that. So what I did is I started from the KKT system. On the top I rewrote it, and then I claimed that this is equivalent to the inclusion problem that we see on the bottom. Okay, so for each player, the first row refers to the stationarity condition, just rewritten in 3 terms. And the second row is the replacement of the complementarity condition and feasibility with the normal cone negative G condition that we saw in the previous slide. All right? It's the very same thing. Okay, so now what I would like to do is to ask you to go back to the congestion game. I will put the slide on. And do the steps that we have seen so far. So write down the Lagrangian functions, and write down the KKT system, and turn the KKT system from its standard form to the form with an inclusion. So you need to work out this trick with the normal cone. Okay? So let's go back, and for simplicity, let's say that lambda 1 is equal to lambda 2, and you can call it lambda. So we have only one dual variable for both agents. So let's go back at the congestion game example. So you have the formulas for the cost functions, and it's here. Okay, so we have 2 cost functions. Constraints are both local within the interval 0, 1, as well as coupled with the limited resource constraint. And I will give you a couple of minutes to try to work it out, and then we will discuss it together. Okay, so you have to go through the Lagrangian functions, and then the KKT system, and then turn the KKT system into the inclusion with the trick we saw with the normal cone. And if you have questions on the way, please feel free to ask. All right, let's check your thoughts on this exercise. Even if you have not finished, let's see if your thought process was what we expected. So let's go to the slide. Lagrangian functions. Okay, we have 3 terms for each player. We have the local cost function, then we have the indicator function of the local constraints. Actually, only one constraint, right? And then we have the term where lambda multiplies the function g. The function g is the one that describes the shared constraint, right? So x1 plus x2, negative 1. So who got to the Lagrangian functions? Okay, very well. And then we had to write down the KKT system. Okay, who tried to work the KKT system out? Someone raised their hand. You tried out with the KKT system?
Yes.
Can you help me writing the KKT system?
I basically wrote I took the Lagrangian of this function.
Which Lagrangian? We have 2 Lagrangians.
The gradient of L1 and L2 for each of them.
Yes.
And the first one treating x1 as a decision variable, x2 as a parameter.
Yes. Very good.
But then writing the cone for the second term to get a little shape.
Okay, so what is the first term then?
The first term is just,
You can write. There are markers.
I'm not going to go to the next slide, so I will let you write.
so basically, I think the first term was a quadratic term, 1/2 x1 minus x1 there.
Yes.
So that basically boiled down to the absolute value of x1 minus x1 left for j1.
Yes.
Plus the second term was like I do a vector multiplication of x1 plus x2 transpose the next one. So it basically boiled down to 2 times x1 plus x2 transpose x1.
Yeah, I thought it was x1 negative x ref squared, and therefore when we take the derivative, we
So
can.
it basically becomes x1 minus x1 left in absolute value.
Okay, and both.
Taking the derivative.
Okay, what about the second term?
And the iota function.
Yes.
Yeah, that's what the variable.
So who worked out the second term in the KKT system? What if we differentiate the indicator function? It's my favorite guy. Looks like it, right? How do we call it in here? Which cone? The normal cone, right? Okay. All right. And well, the third term we had to differentiate with respect to x1, right? So what is left when we differentiate with respect to x1? Lambda. Okay. There was a question there, yes?
Do we have both local cost and congestion cost for J1 or just the local cost?
I'm sorry?
Are we considering both local cost and congestion cost for J1?
Yes. Both.
Okay. For derivative of J1 over x1, I understand the first part of local cost, which is x minus x squared divided by 2. But the other part is the congestion cost.
Yes. There is also that part, and it might be that I forget to write it there. So thank you for asking me. So when we here I differentiated only the local term, but so I forgot also to include the second one. So we need to take the derivative of J1, then the derivative of the indicator function, and then plus lambda is the one left. The feasibility condition, we just rewrote it. And the complementarity is that lambda should be perpendicular to x1 plus x2 negative 1. Okay? And so when added there, the second part of the local of the cost is missing. All right, so now what we would like to do is to transform the complementarity condition with the normal cone operation. Okay, who can remind me the way to do that? We saw that in the previous slide. So how do we replace the inequality 0 less or equal than lambda perpendicular to g?
Defining a binary variable and
Sorry?
defining a binary variable and using the bigger.
We could, but what if I wanted to do it with a normal cone to get a nice monotone inclusion?
You make the normal cone dependent on lambda.
Yes, exactly. So we introduce the normal cone evaluated at lambda. Let's do that in the next slide. So we said that the condition is equivalent to 0 in normal cone negative g. Okay? So we have 0 in, well, let me go here. We have 0 in normal cone negative g. Okay? So this is the function g that describes the coupling constraints. So I just rewrote it here. And for agent number 2, we have the same condition because agent number 2 has the same shared constraints. Okay? All right, so when we put these guys all together here, we have, this term here down here. We have this term down here. Here there should be also the other derivative of the second term that I forgot to include. And then this normal cone is here. Okay, it's in the first line. Then we have the other normal cone here, second line. And the second and the fourth are essentially the same, so I put them in the third line. And what is it? 0 in normal cone, negative x2, negative x1, plus 1. Okay?
What did you say you forgot to put?
I forgot to put the derivative with respect to x1 of the congestion term in the cost function j1. So then it would be here. I only took the local term, like there was no congestion term. So there would be some additional term in here.
Also the previous slide.
Yes, yes. So I think I forgot it to put in here, and then I continued with that. Okay.
Excuse
So
me?
please take a note. Yes.
Isn't it x2 a variable of the Lagrangian x1? Shouldn't you derive it in relation to x2 as well, or no?
So the answer is no, if we look at the first equation, because, let me go back here. So what we would like to do with the first Lagrangian is to take the partial derivative with respect to x1.
Yes, and you don't take it to the partial to x2?
No.
Okay, only to the...
Okay? Because the idea is that each agent has an optimization problem, and the optimality conditions, the necessary and sufficient optimality conditions of that optimization problem refer to its own optimization variable x1 in that case, so the blue one. All right? So this is why we don't do that. Okay, so this is to say that we started off from the cost functions, we wrote the Lagrangian functions, then we wrote the KKT system, and then with some trickery we ended up in this inclusion problem, okay, where we have one term that refers to the local derivatives, one term with normal cones that refer to the constraints, and one term that comes out because of the coupling constraints. Okay, so there is the coupling constraint function, and there is the lambda that is the so-called multiplier associated with those coupling constraints. And there is a question there.
A normal operator in stationarity conditions, because this monotone inclusion only replaces feasibility complementarity conditions, and now we have something n with n in stationarity.
But the stationarity condition is up here, right?
Yes.
Is here, is up here, and it's written down here. So we have two stationarity conditions, one for agent 1, one for agent 2, and they appear in the first two rows.
Why do we have n here?
Because this is the derivative of the indicator function of the local constraints. Okay? So for the local constraints we have a partial derivative, okay? And then for the complementarity condition we have another normal cone because of this trick. Complementarity condition on the normal cone. Okay? So the first two were evaluated at x1 and x2, and the third is evaluated in lambda. All right? Other comments? Other questions? Yes?
Is the normal cone equivalent to the Fortunia map linearization of this constraint? Yeah.
I'm sorry? So
Is that equivalent to the Fortunia map linearization in which you use, other people use the big N method to linearize this term?
I'm not sure if it's related to that. So this is an equivalent characterization, but I'm not sure how, if and how is related to the big M approximation.
So if I ask a question?
Yes, please.
Get back to your matrix for, this one.
This one.
Yeah, okay. So without this trick, a normal cone, you could still write in a matrix form, but the last two will be product rather than plus.
Yes.
Now with this trick, you have three matrices plus. So what do we earn out of that?
Yes.
That's the benefit. What's the benefit?
Exactly. That was my next point. So the reason for having this formulation is that so essentially we have split the terms here in the inclusion, right? And we're going to exploit this splitting in order to construct a computational algorithm that finds a solution. Okay, that finds a vector x lambda that solves this inclusion. Okay, so we're going to see in section number 3 how to exploit this structure to get a solution algorithm out of it. Okay. Other comments or questions? Yes?
In the previous slide that you saw some examples of cones, intuitively, the more pointy
Yes.
the angle is, the larger the cone, right?
I would say if it is pointy, then you have a cone.
If it is pointy, and if the angle is smaller,
The larger the cone.
gets
Correct.
larger. Okay.
Correct. Yes. Correct. All right. So if there are no other comments, so we worked out for the congestion game example this structure where you want to find x and lambda such that this inclusion is satisfied, and the key feature of this inclusion is that you have 3 terms. So you would like to exploit this splitting. And we're going to see a couple of ways to exploit this splitting and generate algorithms that I'm very much sure you're very much familiar with. And so this brings me back to this picture we saw earlier on. We're going to put some math into those blocks, right? So we started off with optimization problems. We wrote down the KKT system and turned into an inclusion problem. So we call this problem a zero finding problem. Find a zero of the sum of those terms. And from there, the next step would be to find an iteration. So update our x and lambda in order to find the solution of the KKT system, right? With guarantees that the x we land at eventually is the equilibrium we are looking for. Okay, so quickly some definitions. We call a point a zero of an operator if x is such that 0 belongs to t of x. Okay? And we call x bar a fixed point of an operator t if x bar belongs to t of x bar. Okay? Again, if you're not familiar with inclusions, just think about equality. Okay? Here are some examples. We know that if a mapping T has some nice properties, for example, is defined from convex set to itself, and it is continuous, then a fixed point exists. While if the domain of this mapping is non-convex or non-bounded, fixed point might not exist. Okay? So this is to say that there are theorems and conditions under which our search for a zero or our search for a fixed point is justified. Okay? In the convex, closed, and convex setup, this is usually the case. So here I will be quick. So there are conditions under which there exists a fixed point of a given mapping, and there are conditions under which this fixed point is unique. For example, if the map is a contraction mapping, so it's Lipschitz with the constant strictly less than 1. So there was a question, in fact, during the break from one of your colleagues, how do we know that there exists a solution to the KKT system? Well, if we turn this zero finding problem into a fixed point problem, we can apply those theorems to see if indeed existence is guaranteed, to check whether uniqueness is guaranteed or not. In general, there might be multiple equilibria. Okay, so here a little exercise, because what we saw is a zero finding problem, right? So we would like to find x and lambda such that 0 belongs to the sum of those 3 terms, right? And I promise you we're going to exploit the structure. Well, the way to exploit the structure is to create an iteration that converges to that solution, and therefore we're looking for a fixed point iteration, right? So eventually, once we find the solution, we would like to remain there. And so conceptually, we need a way to move from, zeros, okay, to fixed points by leaving the set of solutions being the same. And here is one proposition. So I'm saying that the set of zeros of an operator A is the set of fixed points of the operator identity negative epsilon times A. And I would like you to prove that. Okay? So I would like you to prove that if a given x is a 0A, right? So 0 equal to A of x, then x turns out to be a fixed point of this other operator, identity negative epsilon A. So the identity operator is the trivial one. So given x, it returns x. Epsilon is a positive scalar, and A is the given operator. I would like to give you a few minutes to think on how to prove that if x is a 0 of A, then it's going to be also a fixed point of identity negative epsilon A. And this will give us inspiration for our first iterative algorithm. All right, so it's going to be easier than it looks. So let's check your ideas. Okay, so we have statement number 1. x is a 0 of a. I wrote it on the whiteboard. In statement number 2 that says that x is a fixed point of the operator identity negative epsilon times a, where epsilon is a positive constant. How would you go about proving that 1 and 2 are equivalent? Any ideas? Yes?
We can, shall I try that?
Of course.
Just
Please.
say further.
Please. There are markers there.
Maybe an idea is that, suppose there exists an n such that...
Can you use simple marker or...
Doesn't matter.
There is a red one. You might even go to the other board.
I'm ready for you.
So many options.
Maybe we can say that suppose there exists an n such that ax equals 0. Then we can say for all epsilon greater than 0, ax epsilon ax
Correct.
equals 0. And then we can say that what we can have a x plus identity of x is equal to x.
Yes.
And then we can group it.
Yeah. Perfect. Yes. Yeah. So you might want to multiply by negative epsilon, and thank you very much. Very well. Excellent. And so the idea was that here this guy is equal to x negative epsilon a of x, right? And once you see this, it's simple to observe that the two are equivalent, as exactly for what your colleague wrote. Okay, so this is actually the proof. Now, the formulation where I wrote x equal to x negative epsilon a of x inspires us in optimization. Maybe it's good to erase that. Okay, so now you can see a little bit better. Inspires us when we look at optimization, right? Because if we have optimization without constraints and our cost function is strongly convex and say differentiable so that we can take the gradient without any issue and we know the solution is unique when we minimize j, then our operator a in the proposition can be the gradient of j. Okay? If that is the case, then we can define the operator t equal to identity negative epsilon a, okay? And t of x will be x negative epsilon gradient of j. Okay, just by substitution. And this relation might inspire us to design an algorithm that is supposed to work for unconstrained, strongly convex optimization. Which algorithm is that? Sorry? Yes, the gradient descent, right? So if on the right-hand side you put x of k, so you start from a guess x0, on the right-hand side, you put xk in identity negative epsilon gradient of j. And on the left-hand side, you put xk plus 1. Then you obtain the so-called gradient algorithm or gradient dynamics. Okay? So the gradient dynamics is essentially looking for a fixed point of the operator t. And the fixed point of the operator t by means of the proposition that we have just proven is nothing but a 0 of the operator a, which in this very special case is the gradient of j. Okay, so what happens when you find a 0 of the gradient of j, given that j is convex? Yes, we find the minimum. So see, when we wanted to minimize j, which is strongly convex, we turned the problem into finding a 0 of the gradient of j, stationarity condition in our KKT theorem, without constraints. And then we turned this problem to find a 0 of the gradient into that of finding a fixed point. And the fixed point operator is the t we wrote there. identity negative epsilon gradient. And we iterate this t, and if we do that, we get the gradient algorithm, okay, to find the solution of the optimization problem. And what if we have constraints? What changes in this picture if we do have, say, local constraints?
This is substitute J by the first.
Yes, and what nice guy will pop up? Sorry? The normal cone, yes, right? So when we have local constraints in our first inclusion of the Lagrangian, there would be the normal cone. So we would need to find the zero of gradient of j plus normal cone. We saw that in the example. So we're going to need to find the zero of some operator A plus some operator B. And so we need to find a way, let me skip that because here we have already that step. We need to find a solution to the inclusion 0 in A plus B. That's a typical situation when we have constraints, okay? And I would like you to try to prove that, or maybe we can do that together. So again, we have to turn the problem to find a 0 of A plus B into the problem of finding a fixed point of an operator that we're going to iterate, okay? And this should have nice properties. So one way of doing that is via the forward-backward splitting. Okay, so the proposition says if you have a 0 of A plus B, then you can find a fixed point of something. So let's not focus on the details, just the structure. Something which is the composition of two guys, right? So the first guy is this J that I'm going to define shortly. And the second guy is, again, identity negative epsilon B. So something that we have just seen, right? So we are going to put some outer operation on top of the gradient dynamics. Okay, essentially this is what we're going to do. This J here, I need to define it a bit better. So let me go back. This J is called resolvent operator. Okay? So the resolvent operator is defined as the inverse of identity plus A. It's not that easy to grasp immediately the idea behind this resolvent operator, but the result is that the 0 set of A is equal to the fixed point set of J of A. And the proof goes as we have on the slide. Essentially, we do the same steps as before. We write the fixed point of the resolvent. Okay, so first term in the proof. Let me go closer. Okay, so we defined this guy here as an inverse operator. It looks very strange, very weird. We will become clear in a moment. And I'm claiming that finding a 0 of A is equivalent to finding a fixed point of this guy here. Okay, again, we need a way to go from zeros to fixed points. Okay, let's try to prove this out. So let's write the definition of fixed point of this guy. So x equal to this operator evaluated at x. And here the key step is to multiply on the left by this guy, identity plus A, on both sides. All right? So identity plus A here on the left. And when I do identity plus A on the right, I'm going to compose it with its inverse. Okay? So I have an operator and compose with its inverse. Which operator is that? I have an operator composed with its inverse. What's the outcome of the operation? Identity. So that's why here I have identity evaluated at x. Okay, if I do that, I do the math, I get the very same equation as before. I get A of x equals 0. All right? Okay, so for these two bullets, you have to trust me. It turns out that this resolvent operator, when the function that we put in here is the gradient of the indicator function, turns out to be the projection. Okay? So when you have a convex function and you put the gradient of this function as the mapping underneath this resolvent here, then you get the proximal operator. Some of you may have seen the proximal operation. And when this function appears to be the iota function we saw earlier today, so the indicator function, you get the projection. Okay? So in other words, the resolvent operator, when you have indicator functions, is the projection operator. Okay? Okay, so let's go back to our statement here. In order to prove it, we should do the same trickery as before. So we write down the definitions. We apply this guy on the left, on the right. We do the math, and this condition will hold. Okay. So we're saying that when you want to find the zero of a plus b, then essentially you want to find a fixed point of the composition of this resolvent operator. Okay, that in special cases is just a projection, and this other guy, which is called forward operation, this is what generates the gradient dynamics. All right, we saw that before. Your colleague proved that. And so it turns out that when those A and B have nice property, monotonicity, strong monotonicity, then this T operator here, so this composition here, is a contraction mapping. Okay, which means that when iterated, it will converge to the unique solution, which is good. It's good for us. Okay. So let's see how that works in the case you have a constrained optimization problem. So in case that, remember, we wanted to find a zero of a plus b, where b is the gradient of j, and a is the normal cone. Okay, we saw that many times today in the stationarity condition. Okay, so we want to find this zero. We said we can turn it into this fixed point problem, find an x such that this holds. Can any of you tell me what algorithm do they envision based on this equation here? And again, we have an operation that before led us to the gradient dynamics, because b is going to be the gradient of j. And here we have an operation that, when we started off with the indicator function, turns out to be a projection. So what kind of algorithm is that? If we take this equation as an inspiration, yes?
Projected.
Exactly. Excellent. Very well. So, sorry? Projected gradient. Yes, this is what your colleague said. That's exactly right. So inspired by that, we can put x at step k in our iteration on the right-hand side and xk plus 1 on the left-hand side. So here we get xk. This is called forward step. Okay, that's a gradient step. And then if we have feasible constraints, then we project back to the feasible set. Okay, this is what the projected gradient algorithm does, right? So we do a gradient step to reduce the value of the function. We might step outside the feasible region. We need to take a step back into the feasible set. And this is the projected operation, all right? Has any of you seen the projected gradient algorithm before? Yes? Some of you? How many of you have seen the projected gradient as a fixed point iteration that comes from this relationship? Maybe this is less common. Okay? But be aware that when you do the gradient dynamics, the projected gradient dynamics, and many other algorithms, they are the outcome of taking a zero finding problem and turning it into a fixed point problem, and then hoping that this operator here has nice properties, or proving that this operator has nice properties. Okay, so I would like to skip that given the time limitations. It's a homework exercise for you in which I defined a simple network game, and I wanted to ask you how the projected gradient dynamics would look like. So you just had to take the gradient and write down the projected gradient dynamics and put the outcome together into an iteration. So you might look at that as homework. I'm also going to go through that very quickly to say that even when our cost functions are convex and linear, it's not guaranteed a priori that the gradient dynamics will work out. Okay? And this is because we said that in the problem 0 in A plus B, we needed B to be strongly monotone. And this might or might not be the case. In this very special case, this is not the case. And when you iterate the gradient dynamics, you might have persistent oscillations. So be very careful when you select the way you go from finding a 0 to finding a fixed point problem. Okay, I will skip that as well. I have a couple of slides saying that there are many, many other ways to split our operators and go from the problem to find a 0 to that of finding a fixed point. A very popular one is the Douglas-Rutchford that generates the famous ADMM algorithm. And there was another method. Okay, so given the time, I would just briefly mention a special class of games where those gradient dynamics prove very useful. And next, I would like to discuss about a research direction that I think is very promising in case you have multiple Nash equilibria and you would like to find the best one. Okay, so a very special class of games is that of aggregative games, which means that your cost function ji depends on the local variable xi and on some aggregation, for example, the average of the decision variables of all other agents. Okay? This happens in congestion games, right? Because, for example, if I told you that the electricity price you pay is proportional to the overall demand, well, this has nothing to do with the energy demand of your neighbor, but more on the aggregated energy demand across all the network. So a typical feature of congestion game is that they have this aggregative structure, and the structure remains present even if here we put some monotone price function acting on this aggregated demand. And in this work here, we discuss methods to solve those aggregative games based on the projected gradient dynamics we saw today, as well as other splittings that are more efficient. And what I wanted to show here is, again, how to go from the cost functions to the Lagrangian functions, the same exercise you saw before, to the KKT system and to the monotone inclusion. Okay? So if you're interested in those steps, you might have a look at those slides as a homework where I repeat the steps that we did together before. And you should get to those projected gradient dynamics. Okay? Again, those are projected gradient because you have an operator A with normal cones. So when you do the resolvent, you get projections, and you get a B operator that has the local derivatives of the cost functions as well as the terms that come from the coupling constraints.
So your question, the fact that you consider the same lambda
Yes.
for everyone, if you don't do that, does it affect your monotonicity or what?
Yes, it does. Yes. So the fact that here I consider the same lambda, so very good point. The fact that here I consider the very same lambda, and incidentally also in the example that I gave you earlier on, is in order to preserve monotonicity of the inclusion, and the equilibrium you will eventually compute is called variational equilibrium. And there is actually a nice interpretation for using the same lambda, since lambda is somehow pricing or penalizing the infeasibility of the shared constraints by giving the same penalty or price to all agents. You're fairly penalizing them for attempting at violating the coupling constraint. Okay, So there is a notion of fairness associated with variational equilibria, so equilibria that have the very same lambda.
Can you please elaborate why the heterogeneous lambdas make it non-monotone?
Because instead of having, here you see it, so instead of having one function that is which is lambda transpose G, which is convex concave, and here this term here would be monotone. If you have multiple ones, there's no single convex concave function of which you take the gradient with respect to x and the gradient with respect to lambda. While if the lambda is the same, you have a unique function where you do the gradient with respect to x and the gradient with respect to lambda, and this term here turns out to be monotone. Okay. All right. Unfortunately, if you blindly apply the projected gradient dynamics, this guy here might not converge. Who might spot why this is the case? Okay, so I started off with my problem. Let's say I ended up in this inclusion, where I have this operator A, which is monotone, because of there is normal cones. This operator B, which I'm telling you is monotone. Okay? And here I'm applying the forward-backward splitting that gives us the projected dynamics. Okay? And here I'm saying, well, this might not converge. Well, let's perhaps go back to the slide where we had the assumptions on A and B such that the projected gradient dynamics converge. I think it was a bit earlier. Yes. So this was the forward-backward splitting. We wanted to find the 0 of A plus B, which is a fixed point of the resolvent composed with the forward operation, and we needed some technical assumptions on A and B. We needed A to be monotone and B to be strongly monotone. Okay, it's like the difference between a convex function and a strongly convex function. So can you spot anything, any difference between this assumption here and the one we have in the example, in the aggregative game case? So let's go back. Yes? Exactly. So this guy here is just monotone. There is no term in the diagonal that makes it strongly monotone, as you would like to have for the gradient of a strongly convex function. And so since B is not strongly monotone, then this dynamics is not guaranteed to converge. Okay? In order to make it work, we have to twist it a little bit, and indeed it can be done, but you need to complicate a little bit the inclusion problem. Okay? And what I would like to notice here is that well, first of all, these iterations do work. And the difference is here how you penalize the constraint violation. What happens is that you see that each agent is performing a projected gradient step. Okay? This projected gradient step is affected by this lambda that acts as a pricing mechanism. And the way we update this price is essentially by increasing it if there is more constraint violation, or decreasing the price if there is less constraint violation. And so the role of this lambda is to act as a market clearing price. Okay? So the higher the violation, the higher the penalty that the agents see, and vice versa, until they converge to a situation in which there is no more constraint violation because our constraints are satisfied. Okay? As you would like to have. All right, so and those are simulations to show that thanks to the aggregative structure, the number of iterations necessary to converge do not increase with the network size.
Can I ask something about the...
Yes, please.
Why it's increasing in some cases?
Because it's not a mathematical proof that the number of iterations to get epsilon close to equilibrium is constant, but it's more an observation that makes intuitive sense because you have this mechanism where there's only one lambda, the operations that each agent performs is totally decoupled from the others. And there is no communication between agents except for this lambda, which is broadcast to everybody. So you would expect that number of iterations necessary is the same because what you do locally is essentially the same. Okay? There's a mismatch when you use the projector gradient dynamics versus some other smarter ways of splitting A and B and creating a fixed point iteration. Okay, other comments before we move to the conclusion? Yes?
Here you show the plot for iterations for conversions, but what's the computation
For each iteration. Yeah. So in the forward-backward, what you do is a projection, right? That you have it here. And so a projection into a set might be an easy task if the set is, for example, defined by linear inequalities. That would be a quadratic program. If the set is convex but very complicated, that might take more time. So it very much depends on the geometry of the local optimization problems. When instead you, for example, here we have, okay, the forward and reflected backward has more or less the same projection type step inside, so more or less the same computational effort. When you do proximal steps, you optimize at every step a convex function. So again, it depends on the geometry of this local cost function. Okay. When you have linear constraints and quadratic costs, it's very, very cheap. It's a QP to be solved every time. The good news is that it's only local to the individual agent. It's not a projection for the full set that might have thousands or million of agents, and you need to perform a huge projection. It's a large number of small projection steps, which is much better than one projection on a huge convex set. All right, so I would like to conclude. I apologize if I'm a little bit over time. I will skip that. So I would like to conclude by saying that when you have games with convex objectives, then the problem of finding equilibria, in particular Nash equilibria, is equivalent to the problem of finding a zero of some operators that you would like to be monotone. And therefore, you would like to go from that problem to a fixed point problem, because then you can do iterations in order to eventually find a solution. And operator theory and operator splitting are the two key ingredients or tools to do that. We saw that gradient dynamics are relatively simple. Okay, so you take gradients of the Lagrangian terms and you possibly project into feasible sets. There are more involved dynamics, for example, based on proximal operations that are much faster, but require a bit more technicalities to be derived. We saw how to apply game theory into power grids, markets. We saw the traffic example on one slide. And you actually highlighted many other application domains where you have this set up with multiple decision makers. And here I would like to spend one last slide on a very interesting open problem for us. And early on today, it was remarked that, well, the set of solutions or a set of Nash equilibria can be quite large. You might have more than one solution. And I should admit that the dynamics that we have seen and that they are available today are guaranteed to converge to some equilibrium. Okay? And this one, when you have multiple ones, can be inefficient from a system level perspective. Okay? Some of your colleagues, in fact, thought about putting a system level objective as the cost function of the network operator. That's very, very good idea. And so the open problem is, how do we define dynamics, and we prove they're convergent, towards not just any random equilibrium, but to the best one, okay, within the set of Nash equilibria. And we tried to give a partial answer to this question in this recent work where we run an optimal selection among generalized Nash equilibria in monotone games. Okay? So again, if you're interested, you might have a look at our preprint. All right, with that, I would like to thank the team members in my group, both current members and former members, and you for the kind attention. Thank you very much. I'm happy to take questions or comments, remarks. There are a couple there.
So you were talking about less Aggregative, so you didn't really, I think you didn't really talk about what would you define as best
Exactly. What would you do to define best equilibrium?
and fair? Like define, like, for example, in this case where you had two agents and where they both need some, I don't know,
Resource?
some energy,
Yeah.
resource. You want some fairness or something,
Yeah.
so you like give them like as equal amounts as possible.
So what would you like to minimize if you want to make this use fair?
The difference?
Yes. So maybe you would like to minimize some function of the difference between what they get, subject to the fact that x1 and x2 should be Nash equilibria. Among all possible Nash equilibria, find the one that minimizes the unfairness. And that's exactly how we formulated it. So it's an optimization problem that is p-level. So I had a question about that in the break. So minimize a certain criterion, certain function, subject to your decision, the set of decisions you take should be a generalized Nash equilibrium. Very good. Excellent.
Yeah.
There was another question?
So I have like other lectures, probably start from the first order optimality to variational equality, then to fixed point problem.
Yes.
And you start from kind of different rules with KKT, then to a fixed point problem. What are like the difference between those rules? If the red one was a special condition, special case? Or
Those are very similar. Indeed, the idea is to go from the optimization problem to first order conditions, write that as a monotone inclusion, because you stay in the convex monotone framework, and then via the splitting, you get an iterative algorithm to find a solution. A monotone inclusion is a more general class of problems compared to variational inequalities. But when you focus at games and you look for a variational equilibrium, you can very well look for a variational inequality that models the very same problem that we have seen today. Okay, so very, very good mindsets to go through variational inequalities. Who was first?
In terms of the time for convergence, I find it counterintuitive that the time to convergence doesn't increase with the agents, because the way I think of it, you need time for the information to propagate throughout the whole number of agents. It's to say if you've got one agent that has very cheap energy available, that might impact the market clearing price for everyone. But then since you're only doing like proximal information sharing, right, each iteration, or is it centralized? Is it only proximal information sharing, or is there like a centralized way of like redistributing information? Because if it was only proximal,
Let's have a look at this algorithm.
then I would feel like you'd need time for the information to propagate through the whole
That's
network,
correct.
and that the number of iterations would increase the number of agents.
That's
So
correct.
It's already connected in one.
That's correct. So if you had a network game like the exercise that we did not have much time to go through, and you might look at it afterwards at home, then you will see that there are indeed, okay, I cannot find it at this moment, there are indeed, there is indeed information exchange with neighbors.
Yeah.
In that case, of course, if the information has to propagate from one point in the network to some other point, then the larger the network size, the larger you would expect this information needs to get there. However, if we look at the aggregative structure, so aggregative games, and if we look at those dynamics, so what happens is that in the first line, you see a very localized update by each agent. Okay? And you have the lambda variable, which is processed centrally based on aggregate information and then broadcast to everybody.
Okay, so it's not like it's not like alternative direction multipliers with only like proximal. Here you do have like a centralized processing stuff where you redistribute the lambda.
Exactly.
That's why it's
Yes.
okay, then I understand it.
We call it semi-decentralized because all the computation are decentralized and there is only one communication which is a broadcast communication, so you might call it centralized.
Okay.
If you find a slide where there was a network game and you implement the projected gradient dynamics, you will see that there will be a round of consensus-like dynamics and projections. And there, if you run the same plot, you will see that the number of iterations grows as the network size grows.
I think I was misled by the slide that was the like bilateral arrows in between agents, but it's like there is also a step. But yeah, okay,
Yeah.
I understand.
Yeah. All right. Makes sense. There was another question there.
So I guess, so my question was with multiple equilibria, where you know that that's possible.
Yes.
What are the techniques available in searching for those multiples? Is there ways to exclude, once you found a particular equilibrium point, to exclude that and redirect the algorithm to find those?
So I'm not aware of methods in the context of convex monotone games and convex monotone generalized Nash equilibrium problems that find the best or a very specific equilibrium. Of course, you might think that you implement any of those algorithms, you get to an equilibrium. If you don't like it, you discard it, and from there you use another algorithm to compute some other equilibrium, and so on and so forth. Okay, so you do that in a 2-time scale or n time scales, right? You solve for an equilibrium, and until you're satisfied, you keep switching algorithms until you're happy. So I'm not aware of methods that do that in 1-time scale, and this is what we try to do in this work. So we modified a little bit an algorithm which is known to converge to any equilibrium. We modified it with some information about the cost function that you care in the top level, such that in 1-time scale you directly go there. You get to the equilibrium that minimizes that function. We have some conditions like convexity of this selection function, etc. But I think we tried to go for a 1-time scale algorithm under reasonable technical assumptions.
Sergio, I know we are out of the time, but maybe this point is important for people here to connect previous lecture about fundamentals of learning theory and your lecture about fundamentals of game theory. So here it's clear, people, I mean, your agents, you're competing and they have a shared constraint, so you're suggesting approaches, iterative approaches based on projected gradient dynamics, so they find equilibrium. So just trying to connect your method, previous one, also I know you are working a lot on learning in games that we didn't have a chance to, I think maybe next lecture I'll talk about learning in games. So for people, if they are looking for fun problems to work on about learning, so say that if here we assume that everyone knows exactly everything. People knows their own objective functions, they know the shared constraint. So how people they can use learning theory for you? So maybe you can elaborate.
Yes, thanks Jalal for mentioning this point. I had in fact 2 backup slides for that. And I would say there are 2 main lines of research for games where you do not have, where agents do not have all the information they need to evaluate their local gradient. Okay, so one line is called partial information setting. Okay, so agent I does not know x negative I to evaluate its gradient, and therefore it has to estimate this vector via information exchange. Okay, so by talking with some trusted neighbors, agent I has to learn about what is the decision vectors of other agents. And there is some recent literature on that. Here I listed just some of the recent journal papers. The other line of research is that of learning Nash equilibria, or at least some people call it learning because the underlying assumption is that the agents do not have access at all to their gradient. Okay, the gradient they would need to run first order algorithms, and they just measure their revenue function or their cost function. Okay, and this is called zero order information. And through those measurements, they have to learn or estimate what is the local gradient. And people have proposed several techniques to do that. First order filters, higher order filters, extreme shrinking in various forms. So the key aspect is that you combine some learning of the gradient you need and some structure of first order algorithms that you would use if you knew what is your gradient. And here I listed some works that try to dive into this direction in the context of games.
Thank you so much. So let's thank Sergio. Thank you.
Thank you very much.